Okay, we are in our last lesson for chapter 6, linear relations. We are continuing to look at graphing linear relations and what do graphs look like, and maybe what kind of situation would they represent and that kind of stuff. So making sure that you are really thinking about what's going on and what the graph is showing you. Okay, so to start off, you're going to graph the following table. So we have time and we have distance. So I want you to think about what's independent and what's dependent. So time is always independent unless you know how to time travel, which I don't think you do. So that goes on our horizontal axis or the x-axis. And then distance is dependent. And so it's going to go on the vertical axis. Okay, so we've got distance and time. Distance is measured in meters, and in this case, time is being measured in seconds. Okay, and so as you notice, as time goes on, so time, okay, if we're looking, time is increasing by 30 seconds each time, but the distance is not. The distance is remaining constant. It's not changing. Right? So if we were to graph something like this, which you're going to, you would get a graph that looks like this. Okay, and so if we added in another point, okay, if we said 1/8, what would happen at 150? Well, the distance would also be, see, so every point we add in, if we added a point in between, our table's getting bigger. Wah! Okay. There, that's more reasonable. Table got crazy big. And so the distance is not changing no matter what is happening to the time. So we have a zero multiplier. Time is just always equal to a distance of 6. Or sorry, distance is always equal to 6, no matter what the time is. So our equation is just d equals 6. Doesn't depend on anything. It's not changing. So if we look at our second table, again, we have dependent and independent. So distance in this case is independent and height is dependent. So we've got distance and that's going to be, they're just using x. And then we have height. I don't know why I wrote that up there. That's going to be why.
Please excuse the interruption for those teachers that are here tonight for the open house. Bonnie did a wonderful thing and she went and picked up some food.
Sorry, more announcements. Okay, so we have distance and we have height. And so this time when we look at the graph, distance is not changing. Right? It's staying the same. Distance stays the same, but height is going up by 0.5 or half a meter. Okay, so notice that. So then we're going to, so no matter what, if I add another point, right, no matter what, it's at a distance of 1.5 meters, but the height changes. So just a couple different data sets so we can have either a horizontal line or a vertical line. So I would like you to come up with an idea of what kind of situation each graph could represent. And then I would like you to try to come up with the equation for each linear relation. And I sort of gave you a little bit of a clue on the first one if you were paying attention. Or you rewind this, whatever. But I want you to come up with those so we can talk about those together tomorrow. The last thing I want to show you, and so there's some tricks to matching some graphs and equations. Everything we've been working with so far has been in y equals mx plus b form. I know that this means nothing to you. We haven't really addressed this yet, but I'm going to add another page. I'm going to freestyle here. We're going to go rogue for a little bit. So we've always said that, okay. Okay, so we've always said that there has been a coefficient or a multiplier that multiplies our independent variable and then we are always adding a constant. And that can be a positive or a negative. So this plus sign might be a minus sign if it's a negative constant. And this is our dependent. So this form of an equation, there's different forms of an equation of the line. This is definitely the simplest to understand and to graph. But this form of the line we know as slope-intercept form. And so what that means is our slope is this another fancy word for saying our multiplier. And so that's always the value in front of the independent variable or the x. And then we have the constant. And the constant is always going to be some point that's 0 comma something. Okay, it's the point when x equals 0. And so when we were making our tables, I said, look for the point where x equals 0. That's a really important point for us. So that's our constant. That's where x equals 0. That's the point if we look on the graph. Okay, that's the point where our line is crossing that vertical axis or crossing the y-axis. So these are two important points. So we're going to look at a couple examples and try to figure out what the equation is from looking at the graph. Okay, so full screen. I'm going to do like probably the first one for you, and then I'm going to ask you to do the other ones. So what happens is there are two graphs for each, two equations for each graph, okay? So when we look at the first graph, we have a multiplier of 3, so that means we're going up by 3 every time. And when we look at the other equation, it also has a multiplier of 3. So I don't know if you noticed, but these are actually parallel lines. These lines are never crossing. They're going up by the same slantiness. They're the same distance apart all the way along. So that's not really going to give us any clues because they have the same multiplier. What does give us a clue is the constant. So in the first equation, we have a constant of 0. So that means it's crossing at 0. Okay, crossing the y-axis, or when x equals 0, y is also 0. So this has the point 0 comma 0. When we look at our second equation, our constant is minus 7. So that means when x equals 0, y equals negative 7. Okay, so we go to the graph now and look at where the graphs cross the y-intercept, or where they cross the y-axis. And we notice that the first graph, the red graph, crosses at the point 0, 0. So that means this is the line y equals 3x plus 0, or y equals 3x. So that means the blue line that crosses at negative 7 is the equation y equals 3x minus 7. And it would mean, if it has a multiplier of 3, that means it's going up 3 over 1, up 3 over 1, up 3 over 1. And both of them are doing this, okay? Based on the scale of the graph, it's kind of hard to see the coefficient. So what I would like you to do is you're going to try to match up, okay, so these two equations go to this graph, and then so on and so forth. These two equations go to that graph, and these two equations go to the last graph. So you're going to try to figure out which one is each line. I know that you don't have them in red and blue on your notes, but here I'll just leave it on here for a bit if you want to see in red and blue. You can pause it, okay? And then there was this one in red and blue. That one was on there for a little while. And we're going to double check these tomorrow.